Hello, welcome to video number 6, installment number 6, our 6th objective here in section 2.5. So far, when we start learning about lines and planes, we've found distances and intersections between different types of objects. So this is going to be our last intersection video, and then the first intersection that we saw was intersection between two lines. We saw that when we were studying skew lines. And then we took a look at the intersection between a line and a plane. And so now we're going to take a look at the intersection between two planes. So before we get started, let's imagine what would be the intersection between two planes. So what you can do is you can take a look at your laptop and you open it up. And so those can be representing two planes. One plane is the plane with a keyboard, the other one is a plane with a screen. And if you see the intersection is the place where it opens up, it binds. You can look at book as well, same thing. You open a book and the intersection would be its binding. So that intersection would seem like it's going to be a line. And so we're going to find an equation of a line. And what do we need for an equation of a line? We need two things. We need a point and a direction. So that's going to be our task. Okay, in our intersection between two planes, we're going to find a line. And I had to draw this beforehand because it was quite difficult to draw, but it's not very good, but it, I think, illustrates what's happening. Can't even draw a line. So let's draw the line of intersection, and let's assume that that is the line of intersection right there. And so we're going to need a point and a direction from that line. I think I have to admit that this is going to be pretty tough, but out of the two things that we need to find, the easier one is happens to be the intersection. Would be the direction vector. So you need a point and a direction. Let's find a direction vector first. Each of these planes have an identifiable normal vector. So the first plane has a normal vector that's perpendicular to the plane, and then the second plane has a normal vector that is also perpendicular to the plane, and those are normal vectors. Now, what we want is a vector that is on both planes. So we want a vector that is on the blue plane and simultaneously be on the green plane. So we want a vector that is on both planes. So if we want a vector lying on both planes, it has to be perpendicular to the normal vectors. So if we find a normal vector for the blue plane, so for one plane, let's call it N1 arrow, and then the other normal vector we'll call N2. So the direction vector that we're looking for should be the cross product of N1 and N2, because remember, when you cross two vectors, you're going to get a vector that's perpendicular to both of them. And this vector that we're looking for has to be perpendicular to both. So to find this direction vector, let's call it D. This is going to be N1 cross N2. So that will be our direction vector. So once we find our direction vector, we need to find a point on that line. Now, there's going to be several ways to do this. One of the ways to do this is to actually find out where both of these planes intersect a plane like z is equal to 0. In other words, what you want to do is you want to set one of the variables equal to a constant, and the most natural thing would be setting z is equal to 0, but you can definitely set x or y equal to 0, or in fact you can set z is equal to 5 if you think it might make your work a little bit easier. And sometimes people get good at this where they know which variable to set to which constant, and then that would make their job easier after that. But the idea after setting something equal to 0 or any number is that you will not have that variable anymore, and out of the two plane equations that you would have, you will just have two equations and two unknowns. So with two equations and two unknowns, you should be able to solve for that, and then that would give you the intersection between those two planes, or a point of intersection between those two planes. So now let's say we found that point, whatever that point is, and then now we have a direction and a point, and then you can find the equation of the line by just saying point plus t times the direction. Okay. All right, let's do a problem. Here is the problem we're looking at. We have two planes. We have these two planes. So these two planes intersect. Now, there is a possibility that the two planes might not intersect, and the way to check that is to make sure that the normal vectors are not collinear, are not parallel. So just as a quick check, let's check, make sure planes are not parallel. So to make sure the planes are not parallel, we'll get their normal vectors. Let's call this n1 normal vector, or plane 1, and the normal vector is 1, 1, negative 1. You can just see that by the coefficients of the x, y, and z. And for n2, the second plane, the coefficients are 2, negative 1, 3. And just by inspection, you can kind of tell that it's not collinear because one of them is not a scalar multiple of the other. To get, you would need to multiply 1 by 2 to get 2, but you can't multiply this one by 2 to get negative 1. So let's just say it's not collinear, so not parallel. So now that we know it's not parallel, let's go through the action of finding the direction and a point. So let's first find the direction. Direction of the line. So the direction of the line, we'll call that D. Remember, it was equal to N1 cross N2. So this is a cross product, I, J, K. N1 is 1, 1, negative 1. N2 is 2, negative 1, positive 3. So that cross product will give us the vector. So in the I direction, I will have a 3 minus positive 1. 3 minus 1 is 2. In the J direction, there's an automatic negative sign. I have a 3 minus negative 2, so 3 plus 2 is 5. And then for the K direction, I have a negative 1 minus 2, so negative 1 minus 2 is negative 3. So this should be the line or the direction vector for our for that line that we're looking for. Okay, so now we have D, and let's find a point. We're going to find the point on the line, which is saying we're looking for the point of the intersection of the two planes. And remember that we can do whatever we want, and for simplicity's sake and just for algorithmic sake in our heads, just let z equal to 0. You can let x equal to 0, you can let y equal to 5, you can let whatever equal to whatever. The bottom line is that after you do what it is you're going to do, you will have just two variables. So you would have eliminated one variable, and you'll have two variables and two unknowns. So let's let z equal to 0, and then we have x plus y minus 0 is equal to 3, and then 2x minus y plus 3 times 0 is equal to 1. So we have two equations and two unknowns. This is easily solved for by adding both equations. I have 3x is equal to 4, so x is equal to 4/3. So This is what I was talking about in choosing what to let equal to a number, choosing the right variable. Not that it's wrong, but now I have a fraction, and I tend to not like to deal with fractions if I can avoid it. So there probably might have been another substitution that we could have made that would have made this a nice number, but we can get over that and continue our work. We need to find our x, or we need to find our y value. So when x is equal to 4/3, and then we add y, we should get 3. So y is equal to, that would be 9 minus 4, 5, and common denominator 3. So this is our x and y. And don't forget that we originally had let our z equal to 0, so now we have our point. So our point is going to be 4/3, comma 5/3, comma 0. Okay, great. We have a point and a direction, and now we're practically done. Our line of intersection is going to be, I'm going to call it L of t, and an arrow on top because this is going to be a parametric equation or a vector function. The point is going to be 4/3, 5/3, 0, plus t times a direction vector. Direction vector is 2, -5, -3. And I generally like to put t at the end, but it doesn't matter. Okay, so this is it. This is our solution. And now let's take a look at this graphically, because we can. Here are the two planes that we have. We have one plane, we have another plane, and you can see that their line of intersection looks like it's going to be, well, that line, whatever that line is. So let's find our vector. We have a vector, sorry, I'm going to move this, 2, -5, -3. So our vector is going to be 2, comma, -5, comma, -3. Now this vector, which I can't see at the moment, is a vector that's coming from the origin. Well, that's not very useful until I move it to the actual point that I have. So let's get that point involved here, and the point was, I believe, 4/3, comma 5/3, comma 0. And if I look at that closely, maybe make it a little bit brighter, you can see that it looks like it is on both planes, which is great news. And now let's copy that point and make that to be the tail, the initial point of that vector. So physically move that vector to that point, and then we should see that that point, or that vector, now is going to be along that line. Okay, we can see that. And the last step to get to incorporate our final answer is to actually write the equation of the line, and we can just do that using a space curve, and I'll not do that, so I think that's good. All right, so I hope this is helpful, and good luck.